Hi, my name is Cam, and this is Lab 5 for Physics 2211. Introduction, we wanted to predict the motion of a falling slinky and what surroundings may affect its descent. And for the objects, we have the slinky. Predictions, we're using Tracker. And for a computational model to compare, we're using GlowScript. And our purpose is to find why the bottom of the slinky remains mostly stationary at the start of its drop. Concepts we have for this are Newton's second law, where a net force on an object is equal to the object's change in momentum over a change in time, and the force of the slinky is acting as a tension force for the bottom of the slinky's gravitational pull that is acting on it, and here are some equations that might be helpful for this. Some initial conditions: the system belongs directly to the slinky, with the surroundings being Earth and gravity. The initial velocity of the system is at rest, so 0 meters per second for all of the vectors. Acceleration is just gravity. The initial stretch of the spring is 1.246 meters. Its initial position is effectively 0, and its final position is in the negatives, according to the standard graph we used within Tracker. Picture of the data I've gathered in Tracker and what we're using to analyze this, and comparing it to the computational model in the next slide. The picture of the coding that we used for our computational model. Here you can see some of the equations that we wanted to use and enforce for the models to have maximum accuracy to what we'd expect to see in the real world. The comparison of the two models, the observed in blue being our Tracker and the predicted in orange being our computational model that we made in GlowScript. Both models have the common trait of the bottom of the slinky being stationary until the top reaches it, and then it descends down to the surface of the Earth due to the acceleration of gravity. Some human errors that could have occurred during the comparison of the two models of Tracker could be the calibrating of the slinky. Maybe it wasn't perfectly lined up, and then with the tracking itself being it not pointing directly on the bottom of the spring each time during its descent. And some potential errors that could have occurred during the GlowScript model was rounding of the variables or numbers, and maybe a bit of error with the coding itself. The discussion would be why the bottom of the slinky would remain still during the duration of its descent until the top reaches the bottom of it. Would be that the forces acting on the bottom of the spring could cancel out with the gravitational pull affecting it due to the tension force of the remaining upper end of the spring as it's collapsing in. And if we added a weight onto the bottom, depending on the mass of the weight could have no effect on the bottom of the slinky waiting for the top to fully collapse. But if the weight was heavy enough, it could lessen the delay of the bottom starting to fall compared to the top, as the spring would then transmit information through its oscillation and its waves quicker the heavier the weight is. In conclusion, the bottom of the slinky remains at static equilibrium during the beginning and middle of its descent, as the forces acting on it, gravity and tension from the end of the slinky, are at equal magnitudes but are acting in opposite directions. Thank you for watching.